frequency translation and mixing. And we say that in the processing of signals in communication systems, it is often desirable to translate or shift the modulated signal to a new frequency band. So we have the carrier frequency as this, and the intermediate frequency as omega 2. So there is normally that requirement, and we see that the received signal, or now that has been translated, is translated to a new frequency called intermediate frequency. And we see that in that intermediate frequency, it is easier to perform amplification, filtering, and demodulation. And for that reason, therefore, we need to find to process how do we carry out the frequency translation. And we are also saying the device that performs that frequency translation is called the frequency mixer or converter or heterodyne receiver. So there are three terms that are used for the same process. That is, the process can be called frequency mixing or frequency conversion or heterodyning. And we use this kind of mixer. This is the diagram that describes how we perform the mixing. So this is our received frequency, our received signal x of t that has a carrier frequency omega 1 of t. So this frequency is multiplied with another locally generated signal having frequency omega 1 plus omega 2. So this is our desired intermediate frequency, and this is the carrier frequency that was used to translate to that was used to carry our signal, and therefore it was the modulated carrier. And therefore, when you perform this operation, this multiplication, we are going to have two frequency components following the concept of cosine. And I have just tried to give an illustration how this is done. So I'm calling this signal at this time as DT, or the demodulated signal, before filtration, which is going to give us a y of t. And therefore, the dt is a product of x of t and the mixing frequency, which is 2 cos omega 1 plus omega 2 t. Therefore, when we do the multiplication, you end up with cos omega t 1 t times 2 cos omega 1 plus omega 2 t. Therefore, following this identity of cosine multiplication, cos A cos B, because you can see clearly that we can say this is our cos A and this is our B. Therefore, when you perform that multiplication, you're going to end up with two terms of cosine, cos A and cos A minus B plus cos A plus B. And therefore, we can end up with our amplitude remaining as empty, and the other term that is as a result of subtraction of omega 1 plus omega 2 minus omega 1, we end up with omega 2 as on its own, whereas the other term will have the two omega 1s and omega 2. So for that reason, we are passing the DT signal through a bandpass filter that is centered at omega 2, and we can clearly see that this will be cut off. Therefore, for that reason, we are going to be left with DT having only one frequency term, that is cos omega 2t. And that is our desired intermediate frequency or signal that has been translated from omega 1 to omega 2. Therefore, we have d or y of t is equals to mt equals omega 2 of t. So we observe that in the operation of frequency mixing and heterodyning is a common problem that is associated with that. And it is the presence of another image frequency. And we in problem 313 that we shall look at shortly, we see that we desire that the locally generated frequency be 45 kilohertz higher than the incoming signal. And therefore, we suppose that the reception of our AM station at 600 kilohertz desired, what we'll actually find out is that then the locally generated signal will be at will be at 1055 kilohertz, and this is of course equals to here. We desire that at 450 kHz. What I have just brought is just an example that illustrates the kind of frequency mixing that we are doing. We are saying that the local oscillator frequency, which is the one that we feed in at our mixer, is normally the sum of the desired, which is omega 2, and the incoming frequency, which is omega 1. And therefore, when you do the multiplication as we have seen above, you're going to have two components, the desired and another sum that another component that has the mixture of the desired and twice the incoming. This is the one that we filter out at the BPF filter, and therefore we are left with omega 2. Now we are saying another thing. The other thing that we are saying, I have just brought in another illustration that shows how the image frequency of it might appear. Consider here that we said earlier that our incoming signal is coming at 455 kilohertz, and therefore we say that our desired frequency our desired intermediate frequency is 600, and therefore we were able to create a locally generated oscillator that give us the addition of this plus this, and therefore we were able to obtain the intermediate frequency as omega 2 as desired. So having done that, we are now assuming that assuming that another signal exists, or another signal appears which has the frequency centered at 1510 kilohertz, which in mathematical operations is equivalent to twice our first frequency, which was 2 omega 1 plus omega 2. Of course, this is true because 2 omega 1 is 2 times 455 becomes 910. 910 plus 600 becomes 510. Exactly. So we are saying that if this other frequency appears at the incoming signal again, then what we'll do is that when we multiply with our locally generated carrier, which is at omega 1 plus omega 2, we are going to do some operations, as you can see here, that says that we are going to have cos omega 1 plus 2 omega, this incoming, times the locally generated signal, which is omega 1 plus omega 2. And when you perform the cosine multiplication, you are going to find out that the first term, that is of cosine A minus cosine B, like we did, is that it is going to leave you with one cosine term having frequency or center frequency of omega 1, which was at 455. So we were saying that we desired to move our frequency from 455 to 600 kilohertz, our intermediate frequency, but we have generated another same signal that is exactly the same place where we want to live. Therefore, it becomes impossible, as we have noted earlier, to separate those two signals. And that is a concept of the image frequency end. But they're saying that we should aim at avoiding the appearance of the image frequency altogether. And we are saying that we cannot still remove the image frequency by attenuating it using a selective RF amplifier just before the mixing happens. Now, the concept of frequency division multiplexing is quite common, particularly when you want to send multiple or composite signals over a common channel. And we say that to transmit a number of these signals over the same channel, the signal themselves must be kept apart or separate so that they do not interfere with each other, and thus they can be separated on the receiving end. There are two types of multiplexing techniques. One of them is frequency division multiplexing, and the other one is time division multiplexing. We shall be discussing about TDM, I think, in our other unit, not this one. We shall be discussing the TDM. But for now, the FDM is quite common, and we are going to be discussing it in chapter 4 or our next chapter. So in FDM, the signals are normally separated by their frequencies, such that one signal is centered at frequency F1, and another one is separated at frequency F2, and therefore the difference between the first one and the second one is that one is centered there, the other one is centered there. Therefore, there is always a gap between these two, and therefore when you are receiving them, you would only apply a filter that will filter the first one, and etc. etc. So that is the idea of FDM. Now, the spectra of the message signals and the sum of the modulated signals are indicated in the figure 315, which is indicated right here. This is our figure 315. Just as I have mentioned, each of the messages are centered at their own frequencies, but they take the same idea. So, but each one of them is carried by a different carrier frequency centered as C1, C2, and Cn respectively. So for this example, we are working with three signals, each of them modulated by their own carrier, which we shall later see that this carrier can be considered to be the subcarrier. So once you have now combined these three signals that have been modulated or that have been used to modulate this subcarrier, then they are carried by our signal. And once they are carried on the receiving end, we can apply bandpass filters that is centered at each subcarrier. So this one would be at C1, at C2, and at C3. And applying the same principle that we applied when you are doing the DSB, when you apply C1 with another locally generated carrier of the same center frequency, what you end up is one component that has zero frequency or that is centered at zero frequency, and another one that is centered at two frequency that of the carrier. And therefore, when you apply a low pass filter, it removes this off. Therefore, you end up with a message signal that is centered at zero frequency. Similarly, so you are going to be having three messages received on the other head, as long as you have sufficient gap between between this and this, such that there is no spectral overlap over these two over these composite signals. So we say that we normally require that there is sufficient spacing to avoid the spectral overlap, just as I have mentioned. However, the most widely used method for modulation of that nature is single sideband modulation, the one that we looked at earlier. At the receiving end of the channel, the three modulated signals are separated by bandpass filters, just like I have mentioned, and they are then modulated. For FDM is used in telephone systems, telemetry, commercial broadcast, television, and communication networks. Therefore, it is very widely used, and so the former, okay, the usual AM modulation of radio signals, television broadcasting, the analog television broadcasting, all of them apply the FDM signal, the FDM multiplexing technique. And we're saying that the commercial radio broadcasting stations that operate on amplitude modulation use frequency spaced, now carrier frequencies spaced at 10 kilohertz, and the typical range of the modulation signals or carrier, the center frequencies of the carriers are normally centered between 540 to 1600 kilohertz. And this separation of 10 kilohertz is not sufficient to avoid sufficient gap that would enable would avoid the spectrum of the messages overlapping. Then what happens is that the signals that are or the carriers that are closely adjacent to each other, though they are not on the same band, so like this one and this one would still be operated, but they would be one would be operated in a different range. Say Nairobi and another one in Nyeri. Therefore, these two would not interfere with each other because they are separated by two things. One, the distance of geography or the geographical distance, and two, this small gap that separates the two of them. And therefore, the concept of interference is minimized. We also say that the FM modulation signals are separated, or the carriers are spaced at 200 kilohertz apart, and you'll see the reason why. And in long distance telephone systems, about 600 or more signals that are carried by coaxial cable or microwave links can be carried by one link, and therefore their spacing of separation is a bit smaller, about 4 kilohertz apart. So, but in practice, the composite signal may also be modulated by another signal, and for that reason, that is why we end up with the term that we have adopted, that is of subcarriers. Therefore, we are saying that these three, this was carrier one, another carrier, and another carrier. But now the three of them can be used now to modulate another carrier, such that the other carrier now gets the modulated area on the receiving end. So you demodulate. So you perform modulation here. Therefore, once you demodulate, then you are going to be able to apply the bandpass filters to retrieve the subcarriers C1, C2, and C3.